This time we were starting to get the ingredients to construct the quantum representations, and what we ended up defining at the end was the scale modules of free manifold M with maybe boundary and maybe a collection of intervals in the boundary. Here, if the boundary of M is connected, well, here the way you have your intervals embedded in the boundary, the only thing that matters is how many intervals, oriented intervals you have. So you will instead talk about Mn, where here n is the number of intervals. So here we say that this thing would be the quotient of the free module spanned by a frame tangle with n with n boundary points, n boundary intervals on the boundary of M by the Kaufman relations. So I will not write down what this was. And well, today what I will start with is define some specific elements which are the so-called Jones-Wenzel idempotents. So which are elements in the scale module of the ball with two endpoints on the boundary, where n is at least one. So they are defined by the following recursion and will be helpful for computation later, so which is why we are defining them. So the element f, which is the so-called nth Jones-Wenzel idempotent, will be in here. And we'll have that f1 will just be, so I'm supposed to take a tangle with two a tangle with boundary 2 points on the ball. So we'll just take the straight strand. And then I define the nth Jones-Wenzel idempotent by the following recursion formula. So I will write that Fn will be obtained by, right. So I will juxtapose the n-1 Jones-Wenzel idempotent and with a strand, and I add another tangle. So this thing would be a linear combination of tangles with two endpoints on the boundary in a ball, and I add another such linear combination of tangle, which will be the following. So here I put Fn-1 twice, and I add the strand like this. And I add a coefficient here, which is this thing, where this satisfies, well, this is defined like this. Okay, so, well, I'm defining those elements. The reason why we are talking about this element is that we have some nice graphical properties, so which will be helpful for computations. And they will be used to define so-called colored Kaufman bracket, which will be a variant of what we defined last time, which was the Kaufman bracket of framed links in S3. So if I have a link L in S3, and I color all its components by the Jones-Wetzel idempotent Fi. Some Fi, so let's say the ith component, the jth component is colored by Fij. So for example, I could have something like this. So I have here a two-component link, and I say that I color this by I and this by j. This means that my frame link, I replace the first component by, well, first I put a ith parallel cabling of this this component. And I insert the ith Jones-Wetzel idempotent somewhere here, for example. And I do the same for the other. Okay, so this would be, and then I take the Kaufman bracket of this. So here I get bracket of L1 with Fi, union L2 colored by Fj, where L1 would be this component and L2 would be this component. So we can do that, and we can more generally. So this is a knot. This is a component. So so I put, like, I open one of the strands of the component, put an Fi, and it won't matter where I put it. Like, I will get the same thing if I put it on a different strand. It won't change anything. Just because the Kaufman bracket is an isotopy invariant. So if I put the Fi somewhere else, well, I can just slide this somewhere else, and I get the same invariant, because this is just an isotopy what I do. Yeah, so first here I'm doing a cabling first, and then I insert the Jones-Wetzel idempotent. Sorry. More generally, what I can do is we can color a component by a linear combination of those Jones-Wetzel idempotent. So what will it mean that if I have a knot and I color it by some lambda I Fi, and I want to talk about the colored Kaufman bracket of this knot colored by this? Well, I'm just extending this definition linearly. Okay, and for links, we extend multilinearly. Okay, so, well, I'm extending the definition of the Kaufman bracket to such colored links. And the reason is because I'm introducing those Jones-Wetzel idempotent is because of all of those relations. So some of the important relations are, for example, this one. So when you have something colored by Jones-Wetzel idempotent Fn, and you put a twist, then it just multiplies everything by a factor. And this property will be important later, because based on the, we will use those Cohort-Kaufman brackets to construct invariants of free manifolds, and for which we will have to verify that some invariants under the so-called Fenroch moves, which involve particular computing what happens when you change something by a twist. So you have such a relation, which is important. And here you have other relations that, well, are helpful to be able to show this relation. So one relation which is quite important for computation is this one. So whenever you have a strand that goes out of the Jones-Wessel idempotent and comes back, you get 0. And using this relation, well, it will help you compute this one or this one, because when you try to resolve the crossing here, you will have only a few possibilities to resolve the crossing so that you don't have a comeback arc. And well, when you analyze then the coefficients that you get, you see that you get this coefficient here, or here when you put a belt around, you get this coefficient here. Okay. And now the first and third relation, you can prove them kind of simultaneously using the definition by induction, using the inductive definition of the Jones-Wessel idempotent. So I won't do those computations. It's not a very hard exercise, and you can try to do it if you're interested. And I wrote some other relations that I will maybe use later. Okay, so with now that we have that, I will try to define an invariant of free manifold, which will be what we'll need to define later, the quantum representation. So my third part. So fourth. And well, before I define those invariants, I need to talk about surgery representations. So surgery is a way that you can construct many free manifolds. So when using links in free manifolds. So whenever you have L, framed link in M. So the way I defined frame links before, it was an embedding of an annulus, of a disjoint union of annuli in the manifold. But it's actually equivalent to consider an embedding of a solid torus. So sometimes it's called a solid link. But the two notions are actually equivalent. So whenever I have a link in a free manifold, I'm able to construct a new free manifold, which is the so-called surgery on L. Which I will write M of L. And most of the time we will consider surgery on links in S3. So this will give us free manifolds S3 of L. So what is it? Well, I take and I subtract the link L. So I subtract some collection of solid tori that I embed in my free manifold. And then I want to add, well, when I do this, I don't get a manifold, a closed manifold. I get a manifold with boundary since I subtracted some tori. And well, it has as many as many torus boundary components as I subtracted, well, as the number of components of L. So to get a free manifold back, I want to glue something back in, and I can glue back tori, which have also, I glue one per component of L. And the gluing here, to define this manifold, I have to say how do I glue each tori to each boundary component of L. The gluing that I choose is, for each component, is the map that exchange the meridian and the longitude of the solitors. Exchange is meridian and longitude. Okay, so well, as a map from S1 times S1 to S1 times S1, which is the boundary of the solid torus, it would be the map XY sends it to minus YX. I want it to be oriented, so I have to put a minus Y. So we can give an example. When you look at the unknot, so the unknot in S3, which I will call U, I have that S3 of U. When you perform this construction, you get the manifold S2 times S1. Okay, and this is something that you can convince yourself by thinking of S2 times S1. So S2, you can think of it as gluing two disks together. And when you analyze this, you see that, and S3, you can also think of it as gluing two solid tori together by embedding a solid tori as an unknot, and the complement will also be a solid tori. And when you look at what the surgery does, well, you see that for the unknot, you get S2 times S. Okay, so you have a classical theorem of Licorice and Was. From, I think, the 60s, which says that every closed oriented free manifold is of the form S3 of L for some frame link in S3. So I can obtain any closed free manifold by doing surgery on some link in S3. Okay, so, well, this is nice. So we can equivalently think of manifolds as links in S3, except, well, maybe we can get the same manifold in two different ways using two different links. So the link here would be called a surgery presentation of the manifold S3 of L. Yes? So I said that the framing, so as I was doing in the beginning, I was thinking of the framing as embedding not just S1, but an S1 times interval. And what I say is you can make this embedding of an S1 times interval into an embedding of S1 times D2. So I'm embedding solid tori. And, well, passing from one to the other doesn't change anything. So I'm removing the link and I'm gluing back D2 times S1. And I need to specify the map to glue the two boundaries together. So boundary of the old D2 times S1 was a two-dimensional torus, S1 times S1. And the new one that I glue back in, I glue using this map. Yes, yes, that's okay. Okay, so well, we have this theorem and we have second theorem, which makes things more precise. So as we said, there was an ambiguity. We can have several surgery representations for the same free manifold. And we have a theorem by Kirby, which says that two links give us the same free manifold, give our surgery representation of the same free manifold if L and L prime are related by following moves. So I have a move K1, which is I take a link and I if and only if, sorry. Yes, excuse me. So the first move is to add a plus or minus one framed unknot disjoint from the rest of the link. And the second one is, well, you have your link and you have somewhere two strands that are close together, and you do what is called the handle slide, which is to for this strand into a strand that, well, follows the other component of it. Okay, so you have this theorem, and it's a hard theorem that to prove it you need what's called the surf theory, which is the theory of Morse functions and their deformation and the singularity that occur during a homotopy of Morse functions. And well, it's a hard theorem. But you have another theorem, which is Van-Roek, which gives you an alternative list of moves for two surgery representations to give you the same free manifold. So, so basically the first move is the same, it's K1, but we can replace the move K2 with the Van-Roek move. So I have somewhere a minus one framed unknot that circles some number of strands. And this I can replace by, well, I will be able to erase this component, but at the price of doing a full twist on all of the strands. Okay, so this is an alternative version of the theorem of Kirby. So you can replace the second move by this one. And well, this one, once you have the theorem of Kirby, it's not very hard to show this theorem. You can show that these moves and the Kirby moves are equivalent. You can deduce the Van-Roek move from the Kirby moves and vice versa. So if you're interested, you can try to do the exercise yourself. Okay. So I just need the last thing before I define the invariant, which is, well, so those so many of those surgery presentations that give the same free manifold, I will still want to distinguish. I will still want to distinguish some of them, because you can get surgery presentations here that do not have the same. I will want to distinguish them by the signature of the linking matrix of the surgery presentation. So I have the following definition. So if I have M a free manifold and N in Z an integer, I will call the pair Mn an extended free manifold. And I will say that L is a surgery presentation of Mn. If L is a surgery presentation of M, and N is the signature of the linking matrix of L. So the linking matrix of L is a matrix of size M by M, where M is the number of components of L. And its entries are the linking numbers between the different components of L. On the diagonal, you have the self-linking numbers. So it sounds like a weird definition, but it will turn out that, strictly speaking, the Reshetikhin invariant, the way I will define it, will be more an invariant of extended free manifold than just free manifold. So there will be, when I change the parameter n, the invariant will change by some factor. So that's why I will want to have this notion. And also connected to the reason why the quantum representation will only be projective representations rather than just linear representations. Okay, so now I'm ready to define the invariants. So the invariants will be defined using surgery presentation of a free manifold, and then taking a colored Kaufman bracket for a suitable color. So I will explain what this is. So in here, I will take A to be zeta R, which is a primitive 2-half root of unity. Sorry. Okay. Starting now, I will write it. Okay, so here R is odd and at least 3. And so I need to define a kind of magical color that will make the Kaufman bracket into not an invariant just of links, but of free manifolds by, well, making it an invariant that's invariant by Fenn-Roch moves. So I will define omega R, the Kirby color, as omega R is the sum for I equals 0 to r minus 3 over 2 of delta 2i f2i. So f2i is the 2f Jones-Netzer idempotent, and delta 2i is the coefficient that appeared up there. So it's delta n is minus 1 to the n a to the 2n plus 2 minus a to the minus 2 minus 2n minus 2 over a squared minus a minus 2. And so I'm defining this. So why am I defining this? When I define this Kirby color, I have the following property, which is that whenever I take an unknot with framing minus 1, colored by omega r, and here I put some number of strands, or rather I put a strand colored by the F Jones-Netzer idempotent, I will get that this thing is the same as the Jones-Netzer idempotent with a full twist. Okay, so this thing looks exactly like the Fenroch move. And well, when you, it's a relation that you can deduce from the ones that I've written here. So you need both this one and this one. And when you expand the linear combination that the Kirby color is, like omega r is a linear combination of Jones-Netzer idempotent, and you plug in those formulas, it turns out that this is property. So it seems like you almost have what you want. You have at least one of the two moves that seems to be working. You have to check what goes on with the other move, the Kirby 1 move. And for this, well, you can do another computation, which is, well, what's happening for a knot colored by omega r. So I will write u plus, and u minus, the framed unknot with framing respectively 0, 1, or minus 1. And I claim that I have the following formulas. So when I color u by omega r, what I get is, well, it will be the sum of the delta 2i squared for I equals 0 to r minus 3 over 2. But when you compute that, what this is, it's minus r over zeta r squared by zeta 2. And this is something that I want to call eta r minus 2. And if you compute the other two, you get the following. The first one will be of the form eta r minus 1 times kappa r. And the other one will be of the form eta r plus 1 times kappa r. And here this kappa r will be some fourth root of unity. Not necessarily a primitive fourth root of unity, might be a primitive half root or fourth root. Depends on the whether r is 1 or 3 minus 4. Or if 1 or 3 modulo 4. This kappa r is a factor that appears when you compute this. Actually, what you get is a quadratic Gauss sum. And, well, it turns out that you almost get this factor eta r. Sorry, I have a -1 here. This is a +1, -1 here. You almost get this factor eta r, but up to this root of unity. Okay, so now I can define, so I have theorem, which is also a definition, the Witten-Reshetikhin-Turaev invariance. So I have that if M is obtained by surgery on L, I have that the following RTR of M, which I define to be RTR of 1 plus N. So here L has N components. So I take eta r to the 1 plus N, and then I take the colored Kaufman bracket of colored by this Kirby color omega r. I say that this thing is a topological invariant of M. So it does not depend on the surgery presentation. It depends only on the free manifold. Well, here I'm not quite correct. I should have said here I take an extended free manifold. N. Yeah. Sorry. Yeah, I will write M here. Okay, so I get this thing. And here, well, this integer n, well, it has not much of an effect on the invariant. When you change it, you multiply it by a power of kappa r. You multiply it by kappa r to the n. You see here that when I apply the Kirby move k1, when I add a framed unknot with framing 1, well, I'm adding 1 to the signature of the linking matrix. And I'm multiplying the invariant by, so I have one more component, so I have eta r times eta r inverse times kappa r. So I'm just multiplying the invariant by kappa r. So that's the effect of the Kirby 1 move. And yeah, this shows that because we already know that we have invariance under the Fenrock move, we get that this thing is a topological invariant of M. Okay, so we can extend this definition a little bit. If we have that M is from S3 of L, and we have also K inside M, a link, we define the invariant of M with the link K in it. And maybe I take this to be a colored link, color this by C. Well, I will define it in the same way, eta r to the 1 plus M. And I take L colored by omega r and union K colored by C. And I take the colored Kaufman bracket. So I can not only define an invariant of free manifolds, but also of colored frame link in a free manifold. Okay, so we now have this invariant. And as I promised, we will construct a we will extract a representation out of this free manifold invariant. And well, there is a process to do this, which is the so-called universal construction. So it's an idea introduced by Blanchet, Abiger, Masbohm, and Vogel, which, well, I will write down in the case of this invariant, but it's something that you could a priori use for any invariant of free manifold. So we define the following. I take RTR of surface sigma G will be, I will define a vector space as a quotient of a free vector space, well, free vector space, as a quotient of a vector space formally spanned by all free manifolds with boundary sigma. Or maybe I can even say I add a knot in my free manifold, a link rather. So here I get a big vector space, like it's formally spanned by all homomorphism class of free manifold, of pairs, free manifolds and link, frame link. And yeah, with a chosen identification with the boundary, yes. Yes, that's why I write an equal and not just an isomorphic. So here I get a big vector space, and well, I promised you that it would be a finite dimensional representation, so it's not going well so far, but I can do a quotient to reduce the dimension. And what I do is I take the left kernel of some bilinear form defined on this vector space. So the bilinear form is the following. Well, I can define it on, so just because this thing is spanned by such thing, I only need to say what this means on M1 K1 paired with M2 K2. Well, those two manifolds have the same boundary, which is sigma. So I can glue them on their common boundary. I also have an identification, so there is no ambiguity how I glue. So I can get a closed free manifold M1 union M2 along sigma and containing the knot K1 union K2. And I simply take the Reshetikin-Turaev invariant of that. So I get, this defines the bilinear form on the basis of this vector space and by linearity on any element of the vector space. Okay, so this is nice. I define a vector space. And you might wonder why this gives us a representation of the mapping class group. And the fact that it gives us a representation of the mapping class group is purely formal. So, and does not really depend on the fact that I'm using the Reshetikin-Turaev invariant. Here, just with this definition, I have that for any W, the cobordism from sigma 1 to sigma 2, such a cobordism induces a map between those vector spaces. Sigma 1 to RTR of sigma 2, which I call RTR of W. How is it defined? Well, here, whenever I have a manifold with boundary sigma 1, I can glue on it the cobordism W, and I get a manifold with boundary sigma 2. So this is how it acts on the big vector space, but it also acts on the quotient, because it will stabilize this kernel. So here, if my manifold or my linear combination of three manifolds, whatever I take on the right to glue, the invariant that I get is 0. If that's the case, then when I take this one and I glue anything on the right, well, it will be 0 because it's a particular instance of gluing something onto M. Like I first glue W, then I glue a bunch of stuff. And it's a particular case of gluing something onto M. So this map not only acts on this vector space, but it preserves the kernel. So it acts from the Reshetikhin-Turaev space of sigma 1 to that of sigma 2. Okay, here I'm not using anything, any property of the invariant RTR. Okay, and well, from this, you can apply this construction to a particular kind of cobordism. So if you have M in mod of sigma G, you get the so-called mapping cylinder. So which I will write as CF, and this is sigma times 0, 1, tangent union sigma, and here I identify x1 to f of x. Well, I will define my quantum representation on f as rho r of f is RTR of CF. And doing so, I do get a representation of the mapping class group. Because what happens when I glue together mapping cylinder? So when I glue together two mapping cylinders, I get the mapping cylinder of the composition. So I get this thing, and then when I apply RTR, I get that this is a representation. Yes? Yeah, you could also say that. Yeah.
Okay. So this acts literally on this, like the basis up there.
Yes. Yes. You could say that. Yeah. The reason I'm doing this is I will sometimes use other cobordism. Yeah. Okay. So we have defined a representation of the mapping class group. Well, although upon closer inspection, my definition does not really completely make sense. Because what I told you is that the invariant of M is only defined up to kappa R. So if I do exactly this, it does not quite work, because the invariant is defined into only modulo kappa R. So then when I take a linear combination, it starts not making sense to define the form. So to make things really work, you have to define your vector space using extended three manifold instead of manifold. So keep in track the value of the signature of the surgery presentation. And it turns out that you also have to keep in track more information on the surface. You have to add a Lagrangian of the homology of the surface. And I won't really go into those details. But when you do this carefully, you will find out that what you get is a projective representation. Because when you apply a mapping class, you might change your Lagrangian of the homology of the surface. And this twists everything by a power of kappa. Okay, so we have defined some representations of the mapping class group, but you're still left wondering where using this invariant and not any invariant, well, we want to get an interesting representation. In particular, even though I modded that by the kernel of this form, I have still no guarantee that this is finite dimensional. So the main theorem, and with this construction, it would be a theorem of Blanchet, Abiger, Asbon, and Vogel. For any G, RTR of sigma G is a finite dimensional vector space. And I can even describe a basis of this vector space. So you have basis given by the following data. You take H, a handle body of genus G. So its boundary is sigma G. And I will define the basis will consist of some collection of elements of my vector space, which are normally linear combination of manifolds with link. And here I will just have the handle body with some linear combination of link. Each of my basis element will be of this type. So here's my handle body. And my handle body, I can think of it as the thickening of a graph, of a free-valent graph. So this is more or less equivalent to taking a pair of Pensée composition of the surface such that each curve bounds a disk in the handle body. It's not exactly that, but it's almost that. So I think of my handle body as the thickening of a free-valent graph like this. And here, well, I can, using this free-valent graph, I can define some elements of the vector space. And what I will do is, well, I have some edges, and for each edge, I may want to replace this by some Jones-Venza idempotent. So here I put an Fi, so which means also that the edge I will take I parallel cable of the edge. And here I put some Fj. And here I put some Fk. So with this, I can define some elements of the, well, those will be define me some linear combination of links in the handle body. I need still a condition for this to make sense because I need to be able to connect the strands at vertices. And so to be able to connect the strand at vertices, I need some property on the coloring of my edges. So here, if at three edges that are connected to the same trivalent vertex, I have I strand, J strand, and K strand. I need the following condition to be able to connect everything without making crossings. So I need to have that, well, the total number of strands is, well, total number of endpoints needs to be 0. And I need triangular inequality. So I need that I is less than j plus k and the other inequality. And I plus j. Okay, so my basis element will be composed of elements like that. So this guy in this way if C is a map from the edges of the trivial graph to the following set 0 r minus 2, satisfying these conditions at vertices, I get out of it an element which I will call phi c. So it would be, this is the graph gamma, it would be the pair AG with in it the skein element corresponding to the graph called by C. So this thing can be taken as an element of the space RTR of sigma. Okay, so what I say is that I can get a finite basis for this vector space using such vectors. Yeah, the graph is the spine of the handle. So I haven't written exactly what's the basis yet because, so here, those were conditions for me to be able to define this element. I need one more condition for this to be a basis. So I need only to choose one handle body with boundary sigma and one graph. Yeah. So the phi c with C from 0 to r minus 2 and CE plus CF plus CG less than 2r minus 4 if EG and F, EF and G share or are adjacent to the same vertex. Those give us a basis of this vector space. So this is something that we will prove in the next session. And I will end up here.